Hey guys, if you're doing any sort of hypothesis testing, you're going to want to go to the Google Classroom, go to Internal Exploration Resources, and then check out this document here that says Hypothesis Testing for the IA. So you might be brought to hypothesis testing because you're like, okay, I ran an experiment or I collected a bunch of data and I want to see if this data is statistically significant. And the way that you do that is through a hypothesis test. Now, in order to do a hypothesis test, you have to rely upon two hypotheses, right? And the first hypothesis is the null hypothesis, and that always contains an equal sign. And that is saying that, let's say you're comparing the means of two things. The mean of the first thing is equal to the mean of the second thing. That's the null hypothesis. That's saying that there is no difference between the two things. Look, they're equal. Whereas an alternative hypothesis would be, hey, maybe these are a little different. You could have alternative hypotheses that look like this. You could either have the mean of the first thing is greater than the mean of the second thing. The mean of the first thing is less than the mean of the second thing, or they're just unequal, but we're like not sure in what way. Okay. So if you had the mean of the first thing is greater than the mean of the second thing, think about how many tails you would have on that. Okay, so if you wanted to just prove that the mean of the first thing is greater than the mean of the second thing, you would only have one tail here, and that would be your zone of statistical significance, also known as your alpha, right? We would call that the level of significance, okay? And depending on the level of significance that you choose, that little tail there could be pretty small or very, very, very small if you want it to be really significant, right? If you want to prove that the mean in the first sample is less than the mean in the second sample, you would have a test that looks like this. Less than, low, right? Less, greater. And now the zone of significance would be down here, and that zone of significance would be dependent upon your alpha. Then you could have the third case where they're just unequal. We don't really know how, but your zone of significance would be below if they're less than, or above if they're greater than. And just remember that your level of significance will be cut in half now because you have two tails. Okay, so if you chose a level of significance of 95%, your alpha is 0.05. Therefore, the area in a two-tailed test would be 0.025. Okay, so that's what they're talking about by a one-tailed or a two-tailed test. It's all dependent on your null hypothesis. So let's go to step 2. It says determine the level of significance of your test. The significance level is the probability of making the mistake of rejecting the null hypothesis when it is true, also known as alpha. But you can just think about it as setting where you want the zone of statistical significance to be. Okay, so remember, these are dependent on your hypothesis that you wrote, and your level of significance is just like how strict do you want to be in this test. Okay, so this would be like the strictest, and this would be like not too strict. We just want to see if there's a relationship between the two. No one's life is dependent on the results of this test or anything. But whereas think about how you would have to set a really high level of significance if you were, dealing with medication or something where people's lives are at risk, right? So for step 3, it says, so we've written our hypotheses, we've chosen our level of significance, we know whether we're going to have one or two tails, and here we are. Step 3 says verify the requirements and calculate the appropriate test statistic. You're going to check with technology. So if you're comparing the means of two samples, you're going to use a t-test. If you're going to try to compare, and that'll be a two-tail t-test, or a two-sample t-test. And then if you're just comparing the mean that you got from your experiment to, say, I don't know, average heights of the U.S., and there's just like a known mean of the population, you would do a one-sample t-test, okay? For comparing probabilities, you're going to use a z-test. So let's say you have the probability of scoring a goal on this team is this probability versus the probability of scoring a goal on a different team is this probability. You want to compare like which team you would perform better on. That's comparing probabilities. You're going to use a z-test for that. And a z-test is just what you know. It's z-scores on the normal distribution curve, okay? Whereas a t-test is just going to be t-scores on a t-distribution curve. And they actually look really similar to normal distribution curve. So it's kind of like, oh, you already know about these. And then no one's doing a chi-square test this time around, but if you wanted to, the distribution would just look kind of like a little funkier. It has like a tail. Okay, so now we're going to calculate our test statistic and kind of quantify our results. Okay, so first you want to check the n and the variance to decide which t-test to use. If you are just comparing a one sample t-test, you don't need to compare the variance in the n's, but if you're doing a two sample t-test, you want to have a matching number of n's so that way you can pool your data. So let's calculate our test statistic. So on the IB, on your like IA paper, you are going to want to calculate this by hand, right? So let's talk about all the things that go into calculating the test statistic by hand. You're basically finding the boundary for your little zones of statistical significance. You're finding the boundaries by hand. Think of it like finding the z-score by hand, but you're in a t-distribution. Okay, so you would have to find the mean of the first thing minus the mean of the second thing. And then that would all be over the square root of the standard deviation of the first thing. Make sure you use the sample standard deviation if you're doing one bar stats. I know how in this class we always use the sigma, but for these calculations, since you're doing a sample t-test, you're going to want to use the sample standard deviation. Okay, so that's for the first thing, and you square it, and it's over the number of items in the first list. And then if these n's are close, like you can still pull your data, it's okay. So if you have like 30 in one and 38 in another, like you're good, it's fine. You're just a kid doing a t-test. So where do you get these numbers from? Well, let's check it out. So I'm going to use sample information from over here. Okay, so I've got two columns. The first column, let's call this mean 1. That's going to come from the runtime it took for a program a kid wrote. Versus mean 2, these are the two means that I'm comparing, is the runtime for the same program that an AI wrote, right? So the kid did 40 trials, and then he got an average time for his program and an average time for the AI's program. As you can see, the AI's program is much faster, right? So if you wanted to see how much faster, think about what kind of a hypothesis you would write for that. Okay, so let's say our null hypothesis is that they're the same. Our alternate hypothesis, though, would be that the computer's is way faster, right? So how would we write that? We would write U2 is greater than U1, or we would write U1 is less than, U1 is greater than U2, yeah. U1, wait, now I'm like, U1 is the kids, right? And it's slower, yeah, the time is greater than, okay, got it, yep. U1 is greater than U2. Okay, so what would our curve look like? It's going to look like this. So when we find our test statistic, it's going to go, let's look at the tails, right? So for U1 is greater than U2, we want to find how much faster this program is. Excuse the kids in the background. We want to find how much faster this program is than the one the kid wrote. Or how much slower. It's weird because we're dealing with time and we like want the lower number, right? So if we're thinking about U1, that is a longer time, and we want to know how much longer it takes for the kid's program to go, which is kind of thinking about how slow it is. Yeah. Kind of confusing to figure that out, but we got it now. So we would go to our sheet and we would calculate the average. So you just do equals average, the column that you want, and then to find the sample standard deviation, you do stdev.s, and then you find it of the column that you want. You do that for these two. Okay, so those are your inputs for the formula here. It's hard to split the screen, so let me put them in the computer first and then I can transpose them over. Okay, so in our calculator, we want to find the t-test statistic. So we would go to a calculator page and we want to go to statistics, stat tests, and then we're doing a 2-sample t-test, and our input method is stats. So for our mean, we're going to do 2.99025, and then our standard, that's 2.99025. There we go. And then our standard deviation is going to be 0.9032717951. There were 40 trials in the first program. And then we've got 2.17375. Standard deviation is 0.2653849405. You can see that the standard deviation is much lower for the quicker runtime too. So we're going to get a pretty statistically significant difference, I think. Let's match our null hypotheses. I forget what it was. It was U1 is much greater than and thus slower than U2 by how much? So U1 is greater than U2. Yeah. Okay. All right. So now this is our output, right? Our test statistic should be, our test statistic should be equal to 5.485. So you can kind of just use the numbers that you pulled from here to put it into the formula, but you're like, okay, so I'm trying to calculate this test statistic on my paper for my IA, and I would get X bar 1 is given to you up here. So do you see how, like, you just have to demonstrate that you calculate the test statistic by hand? You know how to do that. You could say I've pulled these values from my Google Sheet. You can insert a screenshot of your Google Sheet, right? So then you would do 0.9. I'm going to just do ... because I'm just showing you how to do it. I'm not actually doing it. And then this would be for the sampled standard deviation for the second one. Square it over 40. Okay. So if I type that in my calculator, I would end up getting 5.485, right? So I would end up getting my test statistic is 5.48515. So let's quantify that, right? If I want to find the boundary, think about it as a z-score, but now it's called a t-score, right? So if I want to find my boundary t-score for this upper tail here, I'm going to go to the t-distribution chart that I linked in the document that I posted for you guys, and in the left-hand column is my degrees of freedom. So just be careful that I selected a level of significance of 5%, right? So I'm going to be looking at this column here, and that's just because I have a one-tail test. If I was doing my alternate hypothesis was that they're not equal, I would take the area that's in two tails. So I would go to this one, okay, just to be sure. So we're doing a one-tail t-test. We're in the second column over, and my degrees of freedom are going to be the ends in both. That's 80 minus 2, so that's going to be 78. If it was just a one sample, it would just be degrees of freedom is n minus 1. So 78, 1.665. So my cutoff, kind of like my z-score, but we're thinking about them as t-scores now, is 1.6. Where'd it go? 665. So it's 1.665. And I ended up getting a t-score of 5.48. So I'm like, so my program takes way longer to run. And I would say that my p-value is, I go on my calculator, it is, you're going to put a screenshot of this or like take a picture of your calculator's output here to like back up with technology that you calculated it correctly, right? Your p-value would be 2.4969 times 10 to the negative 7th. So it's really, 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 really small, which is good. I don't know. I'm kind of just guessing. What is it? 7th, 1 more 0, 4, 9, something like that, right? So the p-value is very low. If the p-value is very low, it's saying that the probability of this stuff happening by chance is this probability right here, and that's crazy low. So when the p is low, you reject the what's it called? The null hypothesis, okay? So that's how you can just remember. So since the p-value is very, very, very low, also, like if you wanted to kind of dig deeper into this, right, the p-value is, look at this, right, as this probability is like going down as we head towards the right. Like we're saying that a t-test statistic score of 5.8 would be something like this. So that's if we only had 5 trials. That's how like significant it would be. But because we have so many trials, like 78, our test statistic is like somewhere over here. So that's why our p-value is so low. And that's why we say that it's statistically significant, because the likelihood of it happening on its own is like super crazy, would never happen. So what you would say is the p-value is very, very low. Put it all together in a nice little sentence. At the 0.05 significance level, there is evidence to reject the fact that there is that the two programs are equal, and we can see that the program that I created has a much higher runtime, significantly higher runtime than the AI one, so mine is much slower, but now I at least know how much slower. I know that it is a statistically significantly slower amount, so we should probably just use the computer's version. But hey, at least I tried, right? That's what you could say. I don't know. So that's for a t-test. Z-test is the same thing. You would just use a different test statistic and a different chart to quantify your results and find the p-values. All right.